Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 1.13, Removing Discontinuities. We'll do this by looking at an example of a function, piecewise function, where when x doesn't equal 4, we've got this whole top chunk of a function, and when x equals 4, our function's just equal to k. And the question is, for what value of k is our function going to be continuous at x equals 4? Now we can tell this top part of our function really doesn't like 4. X isn't allowed to equal 4 in this fraction. You can't plug in 4 to the denominator. It's definitely undefined at 4. And we know from our previous video on continuity that for this to be continuous at x equals 4, we need the limit as x approaches 4 of the function to equal f of 4. So let's start by evaluating this limit. Now, because it's a limit, we don't actually care what's happening at 4, we care what's happening around 4. So we're going to investigate the top part of this piecewise function as x approaches 4. Now, if we were to plug in 4 to this function, we would get 0 over 0, which means we should be able to simplify it. So I'm just going to go ahead and jump into factoring it. The numerator would factor into x minus 4 times x plus 1. The bottom's got that x minus 4 in it. And now we see that we can actually cancel those out, leaving us with the limit as x approaches 4 of x plus 1. And that's easy enough to figure out. Now we can plug in x equals 4 and see that this function, as x gets close to 4 from both sides, is going to be approaching a y value of 5. And since we canceled out these x minus 4s in our function, that's a removable discontinuity, which creates a hole. We have a hole at x equals 4, and the y value is going to be 5. So that means we have a hole at the point 4, 5. To get a better idea of what's going on here, let's take a look at the graph of this function. After we canceled out those x minus 4s, we're left with just the function x plus 1. Well, that's just a linear function with a y-intercept of 1 and a slope of 1. So that's easy enough to graph. So I'll start drawing it in here. But I want to remember that I do have a hole at the point 4, 5. And this hole is definitely going to make this function not continuous there. But good news, our piecewise function has a solution for that. That's why our piecewise function has this k that's happening when x equals 4. We get to decide what k is going to be. So that's literally just asking us what the y value should be when x equals 4. Well, we definitely want that y value to be 5 because we want the point to fill in that hole and make this function continuous. If that y value is anything else, we're not going to fill in that hole and our function will still not be continuous. As soon as we put the point there, now f of x is continuous at x equals 4 because the limit as x approaches 4 equals the function value at x equals 4. Let's slide over to another example. Another piecewise function defined a little bit differently, defined for x is less than 1, we have x squared minus 3, and when x is greater than or equal to 1, we have this bx plus 1 piece. And we want to know for what value of b is our function going to be continuous at x equals 1. And that should make sense because our functions are jumping at 1, so possibly the two pieces of my function aren't going to meet each other. So in order to make sure this is continuous, I need my limit to exist. But in order for it to exist here, I need to check the limit from the left and the limit from the right as x approaches 1 to make sure the two sides of our function meet. So evaluating the limit as x approaches 1 from the left, that means we plug in 1 to the upper function. We'll get 1 squared minus 3. That'll be negative 2. We evaluate the limit as x approaches 1 from the right. That lets us plug in 1 to the bottom function, and that'll get us 1 times b, so it'll be plus 1. And we know that in order for a function to be continuous at a point, we need the limit as x approaches that point, we'll just call it a, as x approaches a from the left of our function, it better equal the limit as x approaches a from the right of our function. And that's what we're looking for here. We need that to happen. And we already found the two limits, the limit from the left and the limit from the right, which means these two have to equal each other. All right? Then we just make a little equation. B plus 1 has to equal negative 2. we can solve for the appropriate b value that would make the left and right sides of my function meet. So b has to equal -3. So the bottom part of our function could be written as -3x plus 1. Right? And just to clear things all up and make sure we're all on the same page, let's take a look at the graph. This is going to show us that this is continuous. We know how to graph both of these functions. Right? Our top function is just y equals x squared minus 3. Right? We know that's a parabola with a vertical shift down 3 units. So we can go ahead and plot down 3. We can draw our little parabola going in here, making sure to note that it has to stop at x equals 1. In fact, it can't even equal 1, so we do need to make sure that it's an open circle over there at 1. Right? Our second part of our function is -3x plus 1. That's just a line with a y-intercept of 1 and a slope of -3. So if we plot that, we can see starting at our y-intercept of 1, if we follow our slope down 3 into the right 1, we'll go through the point 1, -2, and continue down into the right. And these two sides of our function meet at that point 1, -2. And because the point 1, -2 is on the line, -3x plus 1, and it's where the x squared minus 3 function ends, those two functions meet exactly there. The point exists, so our function is definitely continuous at x equals 1. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.